So today we're going to continue our discussion on lighting systems. It's one of the somewhat rare topics that we spend 2 lecture nights talking about, but it's one of the important ones. So we've talked about the different types of lighting technology, some of the advantages and disadvantages of them. So now let's talk about some ways we can actually save some energy. So if we're looking at some energy conservation measures, ECM, fundamentally, there are two approaches to get at these energy savings. So since we know kilowatt hours is equal to kW times hours, there's only so much we can do to attack that equation. We can reduce the power input by reducing the kW side, or we can reduce the runtime, reduce the number of hours that we're going to be operating our light fixtures. Or maybe we can do both and attack it from both sides and really reduce that electricity usage. The most basic thing you can do is a fixture replacement or a retrofit. So to put it simply, you take out your old inefficient fixtures, you put in some new fixtures that are they're more efficient, they have a better efficacy, and that's really all there is to it. I mean, it's not necessarily easy to do, especially on a big building, but on paper, it's a fairly straightforward upgrade. And with newer technology, so if we're going with LED fixtures, for example, because we can put in fixtures that have a higher efficacy, that can put out more lumens per watt, we can often give better or higher foot candles than before and still use a lot less energy because of that higher efficacy of the more modern technologies. On top of that, we can also see things like improved color rendering index, better relight time. Like I mentioned, the metal halide fixtures take 10 to 15 minutes just to warm up and actually produce a good amount of light. You can put in dimmable fixtures. If you put in LED fixtures that don't have ballasts, that's reduced maintenance. So there are a number of non-energy related benefits as well. And on some of those, like the reduced maintenance, you can potentially put a dollar value on that. You can say, well, on average, before, let's say you were replacing 10 to 20 ballasts per year as they failed, and now moving forward, you don't have to do that. Well, what does it cost to replace a ballast? Just in the cost of the ballast itself, plus the labor of your maintenance staff to do that. So even though that's a non-energy benefit, there's still an argument there for a financial benefit. Sometimes this is very easy to do. Common example in your house or apartment is you take out an old screw-in incandescent bulb, you go to Lowe's or Home Depot and you buy a new screw-in LED or CFL bulb. Nowadays, it's pretty much all LED. CFLs are starting to get phased out a bit, but that's a super easy thing to do. All you need to do is buy the bulb and swap it out. So the basis of savings here is we're going to have a reduced lighting power input. So we're going to reduce the kW side of our equation. Another thing you can do is called delamping, and this is for fluorescent lighting only. And you have to use some caution with this. This would only be recommended if the area you're looking at is already very overlit. They have more light than they need, higher foot candles than they need. And if you do the math and you say, well, I'm going to take out a lamp, you need to figure out what the new light levels are going to be and make sure that's going to be sufficient for your customer. One big advantage of this is it's cheap. You do have to look at your ballast wiring. The short version of it is you have to make sure the ballast is wired to your lamps in parallel. If they're in series and you take a lamp out, you just broken the circuit. But if they're wired in parallel, you can take a lamp out and still have the remaining lamps be powered through the ballast. So there are some wiring potential considerations there. Consult an electrician. Don't do it yourself. Generally speaking, ballast can handle the removal of one lamp. So it's very common to have a 2-lamp fluorescent light fixture, and you could delamp that down to 1 lamp. But it's also very common to have a 4-lamp fixture, in which case you can go down to 3. Basis of savings here, again, we're reducing the power. And the power and resultant energy you're going to save, it's not quite proportional to the percentage of the lamps you took out. So if you have a 2-lamp fixture and you take out 1 lamp, on paper you might think, well, I should be saving 50% of my power there, but that's not necessarily the case, and it's because of that gosh darn ballast. So you still have that ballast power draw that the overall fixture needs to make this thing work. And if you take out one of those lamps, you're not really impacting the ballast power draw. So if you take out half the lamps, you're going to use a bit more than half of the power. The other big one is controls and scheduling. A common refrain that we say in the office a lot: the most efficient system is one that's not running. So the best way to save energy is to turn it off. And that's really true of any system, whether it's lighting, HVAC, whatever. Try to think of ways to turn this thing off when it's not needed. That's always going to be a good idea in terms of saving energy. So with controls and scheduling, the basis of savings here, we're attacking the other side of the equation. Now instead we're reducing the run hours. Some ways to do this: one of the most basic ways to do it is with a time clock. Pretty inexpensive. It's a simple device. You can buy a basic time clock for less than $100 probably. And it's very useful if your building or your space that you put this time clock in, if they're operating on the same schedule each day or week, that's a good use of a time clock, because you want to be able to set this thing and then just leave it alone. If you have a space that has a highly variable use, and maybe sometimes they're using the space at night, sometimes they're doing it in the middle of the day, a time clock is not necessarily a good fit. So that's a basic time clock right there. This would be a mechanical style time clock where you actually have to, you put in these little pins all around the time clock to tell it when to turn on and off. They also make digital time clocks that have a digital LCD display, and it's more robust in terms of its programming options. But it's a very inexpensive way to automatically turn your lights on and off. If you have exterior lights that are outside, say in a parking lot, you can control those with what's called a photocell, which is really just a little sensor that detects light outside. And if it detects light, it breaks the circuit to the light fixtures and turns them off. And then as soon as it gets dark, that closes the circuit and then turns the lights on. So similar to the time clock, this is a very simple device. You buy it, install it, set and forget. Also pretty inexpensive. You can buy this stuff at your local hardware store. To take this a step further, you could buy photocells that have dimmable ballasts, and that would be for fluorescent lighting. I suppose you could use this to control LEDs as well, which wouldn't have ballast. But this is using a similar idea, but on interior light fixtures inside your building. The idea is you still have that photo cell that detects how much light you have inside, and it will dim your indoor lights if you're getting a lot of outdoor lighting coming through the windows. Another term for this is called daylight harvesting. So if you have a bunch of windows that are, say, facing south, and in the middle of the day you get tons of sunlight, you probably don't need to operate all of your light fixtures. And so if you have smart enough controls that can dim those lights, and what you do is you target a certain foot candles. And so that way it's a dynamic change in the light output from your fixtures to give you just what you need. So that that control strategy is a little more complex. You can also use occupancy sensors. I'm sure you've all seen these. You might have been in the bathroom when an occupancy sensor turned off the light on you, which is never fun. But the idea is you turn on the lights when someone enters the room, and then when it's empty and the sensor doesn't see any motion for a certain amount of time, then you turn them off. Sometimes these also have a sound enable. So again, if you're ever stuck in the bathroom and the lights turn off, you can try yelling. And if it doesn't turn the lights on, I guess somebody will just think you're a crazy person trapped in the stall. But maybe it's worth a shot. The idea is if nobody's in the room, you don't need the lights on. So that's your basic occupancy sensor. In this case, it also has a manual on button. So if for some reason it's not turning on, you can turn it off or manually turn it off. If you're leaving the room and you don't want to wait for the timer, you could flick the switch on your way out. And these are going to be best for any rooms that have variable occupancy throughout the day. Conference rooms are a big one in offices because conference rooms tend to be occupied for, say, an hour or two, and then the meeting gets out, and then the room is empty for a couple hours. And then the next meeting comes, and then it's empty again for a couple more hours. So that's a great use of an occupancy sensor. It's not great for any room where you have regular traffic of people. So if you have a common corridor, restrooms, lobbies, any spaces like that where you consistently have people walking through there, that's generally not a good use for an aux sensor. We see these everywhere. It's extremely common. The energy code now says you have to have these for certain space types. I'm not super up to speed on what spaces do require those, but I would guess a conference room would probably be one of those that's on the list. Private offices, that would be another good one because you can have entire days where that person didn't come into work because maybe they're out on a job site or they're homesick or whatever. So that would be another good use for occupancy sensors. A potential synergy here is we can use these occupancy sensors, which are controlling the lighting, but with the HVAC system, sometimes we can piggyback off of these and use these sensors to also turn off the HVAC system that serves that room. And so now you're able to save energy on both the lighting side and the HVAC side. And if they're already installing the occupancy sensor anyway, it's a pretty low cost to also integrate that into the HVAC. A different spin on this is what's called a vacancy sensor. And the main difference with a vacancy sensor is you have to manually turn on the lights, but then the sensor will automatically turn it off when nobody's there. So functionally, it's very similar to an occupancy sensor, except you have to manually turn it on. The idea here is sometimes you can do your work without turning on the light. If you have a private office right in the corner because you're a fancy executive, you get all kinds of sunlight throughout the day, maybe you don't even need to turn on your lights. Or maybe you just pop into your office to grab something real quick and then you leave and you don't need to turn the lights on. So vacancy sensors do give a little bit better savings potential because of that manual on requirement. But with certain individuals, this can be kind of a nuisance because now you're forcing them to manually turn on their lights as opposed to just having them walk in. The most expensive scheduling method we can get is with a building automation system, often abbreviated a BAS. What a BAS gives you is full control over your lighting scheduling at a computer screen. So you can program in your base schedules, say, well, Monday through Friday, these are the hours that people are here, but maybe you have some special events on certain nights or certain weekends that you want to provide some kind of override. So a BAS is going to give you the best control. And for exterior lighting, it's it's going to be better than photocells. The nice thing about photocells is they're super simple. The problem is that can still lead to excessive runtime. So if you have a system that's a building automation system, what you could do is say, I'm going to turn my lights on from 8 p.m. to 12 a.m., but then from 12 a.m. to 5 a.m., I really don't need those lights on. Sometimes you would want the lights on all night long if you had some security concerns, but sometimes you just really don't need to run those lights all night long. So from 12 to 5 a.m., I'm just going to program them to turn off and then back on from 5 a.m. to 7 a.m. as people are getting back to work. So by using a building automation system, I've been able to cut out those 5 hours of runtime every night, as opposed to a basic photocell where it would just run all night long. Building automation systems are pretty dang cool. So here's an example of a building. This is a middle school. And this is the floor plan layout. In this example, this is more focused on the HVAC side. You can see a little legend right here that tells you if spaces are warm or cool or an alarm. So we can see that most of these spaces in green, those are in a comfortable space, but we have some of these yellow spaces that are getting a little bit warm. This repair closet is cool, and something is going on with this admin wing. That is an alarm. It doesn't necessarily tell us if it's warm or cold, but something is wrong there. And then within this, we can see here's what a schedule would look like. So this schedule could be used for lighting control. So we can see that Monday through Friday, 7 a.m., we'll turn those on, and then at 5 p.m., we'll turn them off. Saturday and Sunday, we'll leave them off. But through this interface, we would be able to go in and program in unique events and things like that. Anytime we're looking at some ECM where we're looking at reducing the runtime, so with photocells, occupancy sensors, vacancy sensors, there are some challenges with doing those calculations. Any energy savings associated with those sensors can be fairly difficult to quantify with any kind of accuracy because they're based on people not being there, which is going to vary all over the place. Just because you showed that in this other office building, this conference room was empty 5 hours a day, doesn't mean that that's going to be true at the next office building. So it's going to vary building to building, month to month, room to room. So the best we can really do is estimate those savings. There are lots of studies out there that would show the average savings potential based on the space types. And the good news is, even if you're conservative with those savings calculations, the payback, so the added cost divided by the savings you're going to get, the payback of those sensors is going to be pretty good, which is one of the reasons why the energy code makes you do it on some space types, because it just makes a lot of sense. A quick side note about interactive effects, and this is more of a global idea, but we'll start looking at it in terms of lighting. So the interactive effects of multiple ECMs. You have to be careful if you're looking at multiple ECMs, multiple things that are going to save energy. If you're looking at multiple measures affecting the same systems, for example, lighting, they are going to interact with each other. So let's say we did an analysis and we made one recommendation, ECM1. You can do this on your lighting systems and save 10% a year. Maybe that's something to do with reducing the power. Or you could do this other measure on the same systems. Maybe it costs a little more, but it's going to save you 15% per year. And that's going to be a different measure. Maybe that has something to do with scheduling. But what if the customer decides to do both? Your initial reaction might be, well, they should save 25%, but that's not necessarily true. To put it graphically, let's say our base electric use for our lighting systems is 100,000 kilowatt hours. And we're going to look at our two ECMs completely independent. It's in either or scenario. You can either do ECM1 or ECM2. The first one, 10% savings, that would be 10,000 kilowatt hours. The second one, 15% savings, or 15,000 kilowatt hours. And if you weren't thinking too hard about this, you would say, well, if you do them both, you would save about 25,000 kilowatt hours total. But that's not what's going to happen. If we look at the ECMs analyzed together, let's start with the first one. So we're going to say you're going to save 10%. Well, that means you have 90,000 kilowatt hours remaining or left to be saved on by additional measures. So now that 15%, we only get to apply that to what's left because we've already saved 10,000. So that reduces our savings potential of the second measure. And so instead of 15% being 15,000 kilowatt hours, 15% is only 13,500. And so you have to do kind of a staged approach. Assume the first one is implemented and then apply the second one on top of that. So the combined actual savings here is 23,500 kilowatt hours, not 25,000. So if we add them together, the parent savings is 25. The actual savings will be less than that. So the big point here, you need to be careful if you have multiple measures on the same systems that you're looking at, because this will always, without fail, reduce the combined expected savings. And so if you don't consider those interactive effects, the combined savings will always be overstated. You're going to give your customer a higher number than what they would actually see. And this example was for lighting, but this is true of any system. If you're looking at domestic hot water or HVAC, these same principles would apply. So let's get back to lighting. Indirect heating and cooling effects. We talked about this way back in day one, and now we're going to get into it a little deeper. The heating and cooling effects, very important idea when you're doing lighting savings calculations. And this is essentially our first example of interactive effects, looking at the bigger picture, thinking about if I make this change to this system, what's going to happen to these other systems. As a simple example, let's say you have 10 64-watt fixtures. You replace them with 10 32-watt fixtures. So you would think, well, I just saved half of my power, half of my energy right there. But that's not exactly the case because we have our heating and cooling systems that we have to think about. So as a reminder, light fixtures, if you look around your room right now and you look at the lamp on your desk or the light above your head, that is essentially an electric heater. That just happens to put out light. The purpose of it is to put out light, but fundamentally, it's also putting out heat. And if you're feeding that fixture 75 watts of power or whatever it is, you are putting 75 watts into the space. From the light fixture, some of that some of that power directly turns into heat and some of it turns into light. But as the light hits all the objects in the room, it eventually turns into heat. So for every watt that goes into the lighting fixture, that becomes a watt of electric heat in the space. And that's going to impact our heating and cooling. So if we reduce our lighting load through some combination of energy conservation measures, now our air conditioner doesn't have to work as hard. So we get some bonus cooling energy savings on top of the lighting savings that we've already calculated. But the heating system now has to work harder in the winter. And so now in the winter months, you actually have to pay a penalty for that reduced lighting output. So we have some good and some bad. What's the bottom line? What's the net result? The answer every engineer gives to every question, it depends. Number one, depends on the climate. If you have a predominantly heating climate, like Alaska, where they're running their heating systems year round, well, they probably don't have cooling systems. So any air conditioning bonus savings that you might see, they don't matter because there are no air conditioning systems there, or at least very few, which means throughout the entire year, you're seeing a heating penalty, which is going to derate your savings and make your savings look worse. On the flip side, if you're in a predominantly cooling climate where it's really hot year round, well, they have no or few heating systems. So the heating penalties don't really matter. And you're only ever seeing a cooling benefit. So you get your lighting savings and you get this year-round air conditioning bonus savings. If you're somewhere like Spokane, it's essentially close to a wash. So in Spokane, we can have some pretty warm summers and some pretty cold winters. And so you get a mix. And the net result is going to depend on, well, what is the mix? Do we have more cooling benefit that outweighs the heating penalty or vice versa? It depends. Also, this is going to depend on what kind of HVAC systems and fuel types you have. If you go to a rural school district in central Washington, a lot of those buildings simply have no air conditioners at all, which means there is no cooling benefit there. It might help keep the space a little bit cooler, but they were never running an air condition they were never running an air conditioner to begin with, so there's no bonus savings to be had. Or if you have a building that's heated with electric resistance heat, like electric baseboards, like a lot of old houses have, in those winter months, that electric heating system has to provide an additional BTU for every lighting BTU we reduced. What that means is anytime we're in the winter months, you are seeing zero savings. Because if you reduce the wattage of your lights by 100 watts, well, now your electric baseboard heat has to put out an additional 100 watts. So your net savings is zilch. So that's not a good look. But if your building is heated with gas, you still need to make up that difference. So if you take out 100 watts of lights, you still have to output 100 watts of gas heat. But since gas heat is so much cheaper on a BTU basis, then you still end up with some net positive savings. You're still paying that heating penalty, but it's not as bad as an electric resistance heating system. Or you could have a building that's heated with a heat pump. So as a reminder, heat pumps use a refrigerant system to provide heat. They pull heat from the outside, move it to the inside of your house or your room. But the thing with heat pumps is they have a much higher COP than a regular electric resistance heater. Even though heat pumps are still an electric heating source, that better COP still makes it a lot better. So it's not necessarily a one-to-one basis now on the input side of the equation. So if we reduce the lighting energy by 1 BTU and our heat pump has a 4.0 COP, our heat pump only has to use a quarter of a BTU to make up that delta. So it's still going to skew in favor of the lighting upgrade, even though you are still paying that penalty. It's just the penalty is now only 25% rather than 100% like with an electric resistance heater. There's a reminder from lecture 2, basic heat pump schematic and how it's able to achieve COPs greater than 1. All of these considered, the best case scenario for a lighting upgrade is anywhere that's got a predominantly cooling climate, meaning that I realize that phrase might be a little confusing. A predominantly cooling climate does not mean it is cold. It means the cooling systems are running year round, meaning it's hot. So if you have somewhere like Florida, Hawaii, Arizona, any climate like that where they have air conditioning systems, those are awesome for lighting upgrades because you get those bonus air conditioning savings year round on top of the lighting savings, and there's really no heating penalty that you need to worry about. But the worst case scenario would be a predominantly heating climate where your heating systems are running year round with electric resistance heat. Because every watt you save on the lighting side is just having to be made up by the electric heater, which means you're effectively having no savings at all. So forget about it. Let's run through a quick example. So let's say you're doing a lighting upgrade and you calculate that you're going to save 50,000 kilowatt hours of lighting energy in a year. And that's simply looking at the before and after power draw of the light fixtures. So you run those calculations, the power before, power after, and you assume 4,000 run hours a year or whatever it is. And let's say this building's in a climate, it's a mixed climate where 35% of the time we are running our cooling systems, 45% of the time we're running heating systems, 20% we're somewhere in the middle, and we'll ignore the heating and cooling effects in that middle ground. The HVAC at this building, they have a gas heating system that's 80% efficient. They have an air conditioner with a seasonal average of 3.0 COP, which is 10.2 EER. And they have utility rates, 9.2 cents per kilowatt hour and 76 cents per therm. So that's the setup. Let's look at heating mode first. So in heating mode, we said we are in heating mode about 45% of the time, which means of that 50,000 kilowatt hours that we are saving over the year, 22,500 of that are going to be seen during those heating periods for the 4 months, 5 months out of the year. And so if we are saving those 22,500 kilowatt hours of energy, now our heating system has to make up that difference, because that was heat that was going into the space that's not anymore. So if you run through a calculation, if we convert the kilowatt hours saved, so that's the heat load reduction, convert that to BTUs, we would always divide by our efficiency, because remember, we pay the utility in terms of input. So if our heating system is going to output this amount of energy, we have to divide by our input, divide by our efficiency to arrive at an input, because that's what we pay the utility. Utilities often bill in terms of therms. And so this ends up being a 960 therm heating penalty. So now we have to use more gas than we were using before. Quick side note, in the homework, I know some of you heeded my call to use the insert equation function. This is a very good example of why this is useful. I mean, we're trying to play these gymnastics with our units to arrive at therms in the end. By using the equation function in Word, it's very easy to see how the units all cancel out. So that's the heating side. On the cooling side, we run through a similar process. So our total lighting savings, 50,000 kilowatt hours, 35% of the time we are in the cooling season where our cooling systems are running. So 17,500 of our savings are realized during those cooling periods. So that 17,500 kilowatt hours is heat we were putting into the room that had to be cooled by your air conditioner that we no longer have to cool. The math on this one is a lot simpler. If we no longer have to cool 17,500 kilowatt hours of heat, we have an air conditioner with a process that is 3.0 COP efficient. If you divide that by the COP, you arrive at 5,833 kilowatt hour bonus cooling benefit. So before the project, that's what the air conditioner had to spend to cool this heat energy. that we've now removed. And so that brings us to the net savings. On the electricity side, we have our lighting savings, just based on the before and after wattages of the light fixtures. We have this cooling bonus. So we gained a little over 10% on our electric savings. And now we arrive at about 58,000 kilowatt hours saved after accounting for the air conditioning savings. But on the gas side, well, we saved more on the electricity side, but now we have to spend more in gas. So we've increased our gas bill by 960 therms. So that will be a financial hit on the gas side. Oh, forgot to make this appear in steps, but so the apparent savings. If we were just looking at this on the lighting savings side, if we took that 50,000 kilowatt hours, multiplied it by our electric rate, we would arrive at $4,600 per year without accounting for any of those HVAC effects. But because we're energy engineers and we're smarter than that, we figured out the air conditioning bonus, the natural gas penalty. We apply the rates to those savings. So on the electric side, we ended up saving a bit more, about 5,100 as opposed to 4,600. The natural gas penalty, well, now we have to pay an additional $730 a year in gas use. The combined actual savings after accounting for all that is about 4,400, which is a little bit less than what we had calculated up here. In this case, it wasn't as prominent. 4.4% overstatement on their savings. But if this was different, if you were in a climate where they were in heating mode more often, or maybe they paid more for their gas and less for their electricity, that can skew this analysis in any way. Last point, and then I'll be wrapped up for today. You have to be flexible and adaptable on your units. So this kind of piggybacks on what I was just talking about with the insert equation function and using that to actually see where your numerators and denominators are. When you're talking about cooling efficiency and cooling equipment, they don't typically give you the efficiency in terms of COP. That's what we used in my example. I just told you it was a process that had a 3.0 COP. That's not typically how it's expressed, though. They're typically going to give you something like EER or kW per ton, but those metrics can be converted. So if it were me, I would convert those to COP. COP is the easiest metric to work with because it's unitless. So once you have it in COP, it just makes things a lot simpler. But efficiency and COP are not necessarily the same thing, because you can have a COP greater than 1. You cannot have an efficiency greater than 100%. But in terms of our equations, in terms of input and output and efficiency, COP and efficiency are functionally the same when you're doing these equations. The other confusing bit, though, is heating efficiency can also be expressed in terms of COP if you're looking at a heat pump. And that is standard in the industry. A heat pump is often expressed in terms of COP. So this is somewhat of a preview. We'll have a couple more lectures on heat pumps later. We got about close to 30 minutes. Any questions before we wrap up? All right. I will stick around as long as anybody else is sticking around. Otherwise, have a good weekend, and I'll talk to you Tuesday.